In this lesson, we're going to talk about the kinetic molecular theory and how it applies to the behavior of gases. Okay, so we started out our lessons on gas laws talking about the ideal gas law, or PV equals nRT. We never really defined what an ideal gas actually is. So an ideal gas is a gas that obeys all the assumptions of the kinetic molecular theory. And the next question, of course, is, but what is the kinetic molecular theory? And that's what we're going to go into right now. So the kinetic molecular theory is a series of assumptions that are made about gases. And we'll just go through them one at a time. So the first assumption that we're going to make about gases is that they move randomly in a straight line until they hit something. So if I have a gas moving around inside a container, it's going to continue to hit the walls of that container and move in a straight line until it hits the walls. Right? Okay. Or another gas molecule. The second assumption is that the gas molecules have negligible volume. So negligible means it doesn't matter. So if I have a bunch of gas molecules inside a container, they're moving around in random motion, they're far away from each other, they really don't experience any consequences of their size, right? Unless I have a ton of gas inside a container, it's just that gas is just going to fill up the container. Those gas molecules are going to get as far away from each other as possible and just move in that random straight line. All right, so we can actually say they exist as points. They're really tiny anyway, molecules, but this assumption says that they have no actual volume. The third assumption of the kinetic is that gas molecules have no attractive or repulsive forces. So the repulsive forces, the fact that they're so far away from each other, they don't get in each other's way, they can't repel each other, they never get close enough to each other. I could imagine gas molecules, if they were close enough, they might be attracted to each other by all the intermolecular forces that we had talked about before. And it says that that attraction just doesn't happen. Collisions are perfectly elastic. This means that no energy is lost during the collision. So if I have a gas molecule and another gas molecule attacks it, hits it, it's just going to bounce off, and there's no loss in energy when those attacks happen. All right, with these assumptions, we can draw some conclusions about the behavior of gas molecules. All right, so the conclusions that we can make is that the volume of an ideal gas is the volume of its container. That makes complete sense. If they're moving around in constant random motion, they're just filling up the container. And you already know that about gases from middle school. They'll take the size of their container, and this is true because of the kinetic molecular theory, that statement that they're in constant random motion. Okay. The pressure of an ideal gas is related to the number of collisions of particles. So we're really defining what pressure is. Molecules colliding with the walls of a container result in pressure on the walls of that container. And the last one is the temperature in Kelvin is proportional to the average kinetic energy. And we've mentioned kinetic energy before. Let's get rid of this. Kinetic energy equals 1/2 mass times the velocity squared. All right, and if the temperature is proportional to the kinetic energy, That means as the temperature goes up, the kinetic energy also goes up. This is the directly proportional relationship. And if that's true, if the kinetic energy is going up, the mass doesn't change. The mass is a constant for whatever gas we're talking about. That means the average velocity is going to go up. That means the molecules are going to move faster. All these conclusions, these assumptions in the kinetic molecular theory, we can use to explain all the gas laws, and that'll be the subject of another video coming shortly.